Our lesson goal for today will be taking the square root of non-perfect squares. We learned how to determine between what two integers a square root of a non-perfect square lies between. Today, we'll learn how to find a better approximation. Our second goal is, just like we saw quadratic equation in this form, x squared equals 16 by taking the square root of both sides, getting the absolute value of x is equal to 4, so then x is equal to plus or minus 4. We will learn how to solve cubic equations in this form by taking the root of both sides, and x is equal to 3. Remember, when you see a 3 here, that means it's a cube root. When you do not see a number, it's understood to be a square root. By the end of this lesson, I'll be able to classify, graph, and compare real numbers, find and estimate square roots. How can I estimate the square root of a non-perfect square? The cube root of a positive number p is x if x cubed is equal to p. There is one cube root for every positive number. For example, the cube root of 8 is 2 because 2 cubed, which means 2 times 2 times 2 is equal to 8. The cube root of 1/27 is equal to 1/3 because 1/3 cubed is equal to 1/27. The symbol, called an index, indicates the cube root. Cube roots are not bothered by a negative under the radical symbol. The cube root of 1 is equal to 1 because 1 times 1 times 1 is 1 cubed, which is equal to 1. Our next perfect cube is 8. The cube root of 8 is equal to 2 because 2 times 2 times 2, which is 2 cubed, is equal to 8. Our next perfect cube is 27. The cube root of 27 is 3 because 3 times 3 is 9. 9 times 3 is 27. 3 cubed is equal to 27. Our next perfect cube is 64 because the cube root of 64 is 4. 4 times 4 times 4. Remember, 4 times 4 is 16. 16 times 4 is 64, which is the same thing as 4 cubed, which is 64. Solve each equation for x. Take the square root of both sides. So we will take the square root of the left side and the right side. On the left side, we'll be left with the absolute value of x is equal to 7 on the right side. When we're trying to solve this particular problem, you have to think of what numbers are 7 units away from 0. In this case, positive 7 is 7 units away from 0, as well as negative 7. X cubed is equal to 64. So now we have to take the cube root, but you have to make sure you write that index of 3, and then the cube root. So in this particular case, we're left with just x. You do not have to use the absolute value because underneath a cube root, you can have a negative. And in this case, we'll have the cube root of 64 is 4 because 4 times 4 times 4 is 64. Take the square root of the left side and the right side. Here, we have a negative underneath the radical. Anytime you have a negative underneath the radical, we will write no real solution. Later on, as you move on to Algebra 2, in high school, you'll learn how to work with negatives underneath the radical. So that's why we didn't say no solution, we said no real solution because this negative under the radical is not a real number. Let's take a look at this time. We'll take the cube root of both sides. And in this particular case, we're left with x is equal to, and in this case, the cube root is not bothered by a negative underneath the radical. This would be negative 3. Let's check. Negative 3 times negative 3 is a positive 9, and 9 times negative 3, remember a negative times a negative is a positive times a negative is a negative 27. So this is true. If we try to do it for this one, 9 times 9 is 81, and negative 9 times negative 9 is positive 81. Therefore, a real number times itself will always be non-negative.
Sphere, 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 sphere.
What number times itself and then times itself again is 8? And that answer would be 2. 2 times 2 is 4, times 2 again is 8. The cube root of 27 64ths. In this particular case, we'll look at the cube root in the numerator and the cube root in the denominator. In this particular case, the cube root of 27 is 3. The cube root of 64 is 4. So your answer is 3/4. Remember, 3 times 3 times 3 is 27. And 4 times 4 times 4 is 64. Find each cube root. So in this particular case, we would say the cube root of negative 27 is negative 3. And in this case, the cube root, we would separate it as a cube root of 125. Don't forget your index. And then the cube root of 216. So the cube root of 125 is 5, and the cube root of 216 is 6. So therefore we have 5 times 5 times 5. 5 times 5 is 25, times another 5 is 125. 6 times 6 times 6. 6 times 6 is 36. And 36 times 6 is 216. Solve each equation for x. So in this particular case, we will take the cube root of both sides. On the left side, we're left with x, and on the right side, x is equal to 1. In our next case, we will take the cube root of both sides. Take the cube root, take the cube root. So on our left side, we have x, and on the right side, we're looking for the cube root of 27 over the cube root of 125. So in this particular case, we have 3/5. We'll take the cube root of the left side and the cube root of the right side. So we're left with x, and the cube root of 8 is 2. In our next problem, we'll again simply take the cube root of the left and the cube root of the right. On the left-hand side, we're left with x. On the right-hand side, we will be looking for the cube root of 64 over the cube root of 343. So in this particular case, we have the cube root of 64, which is 4, and the cube root of 343, which is 7. X is equal to 4/7. In this next portion of this lesson, we will learn a technique to estimate the square roots of non-perfect squares. Step number 1, find the nearest perfect squares to the radicand and take the square root of those perfect squares. The square root will be between these two integers. This is what we learned in our previous lesson. Step number 2, find the difference between the radicand and the lower perfect square. Find the difference between the two perfect squares. Step number 3, write the difference as a ratio. Divide to rewrite the fraction as a decimal to the nearest thousands. Step number 4, combine the smaller integer found in step number 1 and the decimal part for an estimate of the square roots. 8 plus 0.471 is 8.471. If you were to use a calculator, you would see that the estimation was pretty close. In the tenths place, but not the hundredths place. If we wanted to round this, they both would be rounded to approximately 8.5. But if we wanted to round to the nearest hundredths, our estimate would be 8.47 off by 2 hundredths. It's kind of like what we learned for pi. Remember, we know that pi continues forever and ever because it's an irrational number. It never repeats and it never terminates because pi is irrational. We cannot write irrational numbers as a ratio of two integers. Irrational numbers are non-terminating, non-repeating decimals, but we usually approximate pi as 3.14 or 22/7. 22/7 cannot possibly be pi because pi is irrational and 22/7 is rational. And we know this because we can see it's repeating. It's repeating after 6 digits. 142857, and it's going to start repeating 142857. When we take a look at pi, we can see that right here at the thousands place, it goes off. But it's good for the tens and the hundreds place. Let's try another example. The square root of 55 is between what two perfect squares? This would be the square root of 49 and the square root of 64. Notice that 55 is between 49 and 64. Therefore, the square root of 55 is between the consecutive integers 7 and 8. Our next step is to find the difference between the radicand and the lower perfect square, and to find the difference between the two perfect squares. Our third step is to write the differences as a ratio and divide. Last and final step is to combine the smaller integer found in step 1 and the decimal part for an estimate of the square root. Therefore, we can estimate the square root of 55 as 7.4. If we used a calculator, it would be 7.416198. For the first tenths, it's spot on, but if we continue to the hundreds, we'll be off by 2 hundredths. I think that's a pretty good estimation. If we want to get a better estimation, we might have to square it. We square it to see if it gets really, really close to 55. Then I would square 7.41 squared and then 7.42 squared. Notice from here to here, we went from less than 55 to more than 55. So we know it's going to be either 7.41 or 7.42. When we find a difference, we see that 7.42 is the closer approximation. It's 0.05 more versus being 0.09 less. This concludes the lesson for today.